Good morning. Welcome back, everyone. Hopefully you had a good spring break. So before we continue with our lecture today, I want to remind you of our upcoming midterm 2. Will be next Wednesday, April 14th, and it can be accessed on submitted on Gradescope. So if you're seeing my screen right now, you can access it directly from your Blackboard course. You can see on the left-hand side, there is a link called Gradescope, and you can click that and will directly send you over to the Gradescope. And you could just do the same thing, take a piece of paper and write your solutions and upload it. And I believe Gradescope even allows if you upload problems one by one, so you don't have to compile everything into one file. You can, if there, let's say you have 6 problems, have 6 pages, and you can just upload all 6 pages, and they will ask you to pick, match the problem. This page is for problem 1, this page is for problem 2, and so on and so on. Okay. It looks very straightforward, and it's easier for me to give your graded exam back rather than sending emails to everyone. So let's try that this time. I believe it's pretty straightforward. Okay, so the upcoming exam practice exam as well as the solutions are already on Blackboard. So I encourage you to, if you haven't worked it out, try to work it out, and you can look at the solution after you worked it out. Okay. The content will be on chapter 3 only, okay? Chapter 3 of Griffiths. All right. The time limit, yes, it will be 2 hours the same, but I added 15 more minutes, so it will be 2 hours and 15 minutes. So the 15 minutes is extra time for you to upload, okay? Yeah, thank you.
The midterm will be on only chapter 3, you said?
Midterm 2 will be only chapter 3 content, yeah.
Okay.
Any other questions?
Is it going to be the same as it's only going to be like 3 response questions and roughly 6 questions like last time?
Yeah, same format.
Okay. Thank you.
Thank you. Okay. All right. So let's go ahead and continue with our class, magnetostatics. So we're exploring B field in a static situation. So we say the source for the B field is, oops, let me get this connected, just 1 second. The source for the B field is steady current, right? If you have a current, then that will produce a B field. And we also derived the relationship. We start with a line current, so currents. Start with one line, right? With lambda, and we derived I as a with a direction that's moving in the direction of the where whatever the positive charge is moving, that is the direction of your current, is N times Q times V. Okay, so we will encounter this N multiple times. That's called a number density. So N is here in the line, indicate the number of charge carriers per unit length, right? So it's a number density. Later on, we will have number density for 3D and 2D. So here is just 1D. How many charges do you have per length? And then if you multiply by the Q, each of the carrier carry this much coulomb. So that's the total amount of coulomb, right? So N times Q times V. So if you were interested in the force as collectively on a chunk of wire, so if you look at a section of these and you want to see, okay, what is the force, Coulomb force, Lorentz force is QVB for one single charge. If you're looking at F on a chunk with a collection of charges, right? And that's going to be N. So here is number of carriers per length times DL. So that's the entire how many number of charges do you have in that length times Q V cross B, okay? All right, so I'm going to move my vector sign. So this is sort of what we like to do. I don't like to put vectors on top of I, and I don't like to put vectors on top of V. So instead, we will put the vectors on the length L, okay? So I'm gonna write a dl V vector as V magnitude times dl vector. So I'm gonna do that. So I can rewrite my force using N times Q times V dl cross B, okay? And NQV, you can see it's just our current I magnitude. So it's I dl cross B. This is probably something you're familiar with, right? This is the Ampere's force. Ampere's force, which is the force on current carrying wire. Okay, so notice that we said magnetic forces cannot do work on individual charges. That is absolutely true. However, you can see as a collection of charges, magnetic force can do work on a wire, a current carrying wire. There is no conflict in there because you can check the chapter in Griffith. They have a very nice discussion and break it down into how do we resolve this. Looks like a paradox, but it's not. It turned out, if you look at the Ampere's force, this force is a component of the force on the individual charges. If you look at the total force done on the charges, it's still zero. It's just as a component of that, there is some work done on the individual wires, on the wire, but there is no work on the individual charges, okay? So if you're interested, you can go to Griffiths to look at how they break down the motion of the wire and the motion of the charges. Okay, so that is the force, right? Remember Ampere's law, we have BIL as in introductory physics, if you still remember that equation. So that's how we derived it. We also talked about, well, it's not always just a line of charge. Sometimes you have, of course, the current flowing through a volume, right? Volume density, which means that current flowing through the cross section dA. And we defined volume density J as in dI over dA. It's called volume density. However, it is current over area, okay? And we discussed that's because current already occupied one dimension because it's only the charges flowing in one direction that give you current. All right, so now if you have an area that is sort of flowing through this kind of area, that's okay. We're going to look at a perpendicular area as the one that matters. So if this is dA, we need to look at what is dA perpendicular, right? So dI would be J times dA perpendicular, which is J dot into dA. You can see it's a dot product between J and dA, which makes sure that we are only looking at the perpendicular cross section. Okay. So there is also a relationship between your current density and velocity. So if we have, previously we used lambda to represent the density, here we have rho. So this is your density, meaning that you have this many charges per unit volume in this region. That means in 1 second, how many pass through? So let's see. If it's moving with a velocity v, and in 1 second, it passed through this much length. And if you multiply length by area, you get volume. You use volume multiplied by volume density, you get the total amount of charges. So this much charge passed through in a second. So this is your current, right? So this is the number of charges. So current is charge over dq over dt. So it's going to be this many charge over time. You said it's 1 second, right? So that's your di, and di is also j dA perpendicular. So if I look at cancel out dA, and 1 second, I get j is equal to rho times v. So as we had before, if you don't want to write rho, but you want to use the number density instead. So if this material has this kind of number density, that is n, represent number of charge carriers per volume. Okay, so if you have this much charge, so the total charge will be n times q. Sorry. Because n is the density, so this is going to be a charge density, right? This gives you the charge density. So you changed number density to charge density, simply multiply n times q. So j is going to be, instead of writing rho, you write nq, that is your new density, charge density times v. J is nqv, okay? So for the 3D situation, we call this 3D because J is flowing, the current is flowing in 3 dimensions, right? In 3-dimensional space. So in this situation, if you look at a collection of charges and see what is the force acting on the collection of the chunk, so dF is going to be n times d tau times q. N is again number density per volume times d tau is you have this many charges, let's say 10,000. So this many numbers times each of them carry this much coulomb. So this is the total amount of coulomb you have. So n d tau q v cross v. Again, n q v is j. So n q v is j. So you get j cross v times d tau. Okay. So previously we had I dl times v cross v. Here we had j cross v times d tau. So this is for 1D situation. 1D. This is for 3D situation. Okay. We also have obviously a 2D situation. Now let's look at those. For a 2D situation, so it's when current is flowing on the surface. So when you have charges simply distribute themselves on the surface. So charges live on surfaces. And we define a surface current density. Okay. So let's take a look at this. You have XY plane. Let's call this X and Y. And you have current flowing on the XY plane in positive X direction. And the cross, it's not the cross section, it's not the cross length, cross distance. The current is flowing is called DL perpendicular. So we call the current density, surface current density K, and we define, let's define K as in DI over DL perpendicular. Okay. All right, so at this point, let's take a look at the application of this concept in a particular question. So here we have a current flowing down a wire with a square cross section. So sort of like a rectangular tube, but the current is only flowing on the surface. Okay, each of the side with a length A, and the total wire has a length L. Okay, so how do we represent the surface current density if if we know the total current is I? Okay. All right. So this is the first question for our current density. So I'll let you go ahead and discuss. For the next couple of questions, maybe we'll just vote right here. Okay. All right. So maybe a minute or two, and you can go ahead and join the breakout rooms.
Dr. Ryan, do you mind if I peek at your notes right before this slide?
Yeah, of course.
Okay, thank you.
Okay. All right. Just any last minute vote? It looks like I got majority of the vote already. Just a few seconds. All right. Okay, so let me go ahead and close this. We'll take a look at your results. So this is what we have. I think we can first figure out which ones are not going to be correct by looking the dimension, and then we can figure out, okay, exactly what we need to divide it over. Okay, so actually a most popular answer is A, is current over area. Okay, so would that be the correct definition for surface density? Recall, what is the current over area? Current over area is what? Is J, right? This would have been correct if the current is flowing, filled within the volume, if the current is flowing through inside the wire. But here it says the current is only flowing on the outer surface. Okay, so we need a surface density, which means we have to divide it by the length. So now the question is, what kind of length should we divide it by? What do you think?
I would say the width, since we care about the width that's parallel to the current flow.
Okay, the width, would it be the A then?
Yeah, I guessed answer B, so Q equals I over A.
Okay, so if I have, let's say, okay, this long wire is has a square cross section. So you can think of the long wire has 4 sides. I'm gonna look at the sides that's facing us, okay, and then their current flowing through it. Yes, it is crossing this width A. I agree. Okay, but then there's also this side. Let me look at this side. You have, I'm gonna use a different color. So this side has the same kind of surface current flowing through, and that's also A, right? And you have the side that's on the back, have some current on the back, and that's also A. You have the side on the left-hand side, and that is also A. So all 4 sides has current flowing across them. So what is the DL perpendicular?
It would be C.
Yeah, it would be 4A. Very good. Imagine if you cut it somewhere, if you manage to cut it and kind of expand it over and become a really long sheet, then you are having this current flowing through the entire length. That's 4A, right? So it's I over 4A, which is correct. C is correct. Very good. Thank you, Jennifer. Okay, so perhaps this question will help you if you were still a little bit confused on the previous question. I think after this question, you should be good to go. So here we are showing, let's say, a ribbon wire, and if you want to know what a ribbon wire looks like, something like this, kind of flat. Okay, and this is we can model this using current density. That current is only flowing through the surface. So let's say you put right next to a ribbon wire, you put another identical ribbon wire, and each of them have a length width of A. Okay. So collectively, what is the new total surface current density? All right. I'll let you go ahead and vote. Feel free to take a moment to think about it before you vote. So be a little bit careful of what it's asking the density. So imagine you're planting trees, right? You have 2 streets. You have a one way of how dense you want to plant your trees in one of the streets. And you do the same thing for another street. And if they ask you what is the density of the 2 streets, what would you answer? Okay. All right, so I'll wait for another 10 seconds and then we can take a look. All right, any last minute vote? Okay. All right, so I'm going to go ahead and end this. Let's take a look. This is our results. So it looks like the majority you voted for either, we definitely will have a density change, either double the density or maybe we have a half the density. A few of us choose, you guys choose A, which is the same density. So anybody would like to share their thoughts? You can either talk about what this is by just reasoning, or you can calculate it. You can calculate the density using current over distance. So anybody would like to share their thoughts?
I picked B, but
Okay.
after giving it more thought, I'm actually starting to think that it's A because you doubled the width, but you also doubled the charge, which would not cause a change at all.
Yes, very good. That's a very good reasoning. Thank you, Nicholas. It's like the planting the tree, right? You have more trees now. You have more length. You double the charges, and then that also means you double the current. Very good. So we can take the approach of looking at the definition for current density is, okay, you have K here. So the total current on the first ribbon wire is KA, and you put another KA here. So you have KA plus KA, that's your total current. I total over DL of length L, right? K prime is over 2A. So it's going to be 2KA over 2A, and that's going to be K. So the same as before, very good. Okay, so each of them have the same density. So it's like if you combine 2 materials of the same density, you end up with the same density, right? So the A is the correct answer. Okay, excellent. All right, so got a page. Okay, so we did a little bit detour, explored a few questions related to the definition of current density K as dI over dL perpendicular. Okay, so as we did previously, again, I wanted to derive a relationship of K and velocity. So as we say dI current, how much current you have is going to be sigma, that's your charge density. Again, what is the surface density times the total area? So what is the area? So let's say you have charges moving with less velocity and across this dl length. So in 1 second, it moved for a total distance of v times 1 second. And that is the length. Length times width is your area. And that divided by 1 second is your current. And that's K times dl. All right, so if you get rid of your dl, you get K is sigma times V, okay, as opposed to what we had previously as J is rho times V, right? Okay, also, if you want to rewrite this using number density, so we have 3 kind of number density already. We have the length number density, the volume number density. Here we use a surface volume number density, means the number of charge carriers per area, okay, per meter square per area. So if you do that, K would be N times Q times. Okay. And likewise, we can derive a formula for the force. Force is now going to be N times dA times Q. So N is number of charge carrier per area times the area is the total amount of total number of charges times the coulomb is total amount of coulombs times V cross B. Okay, and again, I'm going to move N, Q, V together and write it using K. Right, so it's K cross B times the area dA. Okay, so dF is K plus B times dA. Okay, so using that, we are now ready to calculate what is the force acting on the surface current wire. So here we have a ribbon wire. We have a surface current density K flowing through a width A. And you put this wire under a external B field that's pointing upward. So now, of course, we know that the direction of the force is given by the cross product between K and B. So how do we calculate the magnitude? So I'm going to write the equation here. dF is K plus B times dA area. Okay, so let you guys go ahead and vote. Now dA means area, okay? Okay, so we'll go for another 15 seconds. Okay, any last minute vote? All right, if not, I'm gonna go ahead and end the poll. Let's see. All right, so this is our results. It's just a direct application of the formula we just derived, the force acting by the magnetic field on a current carrying wire. And this wire is now a ribbon, sort of ribbon wire, with a surface density K flowing through the surface. Okay, so first of all, you have a cross, obviously you have a cross product to calculate between K and B. And in this case, they are perpendicular, right? So K times cross B becomes what? Becomes K times B magnitude, right? Because sines 90 degrees is simply going to be just 1. So it just becomes K times B, and you have a total force, right? So F is going to be KB dA, And you can see K and B they're all uniform. So it turned out it's just going to be KB times the integral of dA. So you need the total area. So A area total, right? So what is the total area of this ribbon wire? It's a rectangular shape, right, with A and B. So it's just going to be A times B. That's going to be the total area. So yes, C is the correct answer. Very good. So KB times A times B. All right, so with that little definition of a volume density and the current density and the surface density, we're now ready to explore Biot-Savart law. So we still remember some of this from our intro physics. Now Biot-Savart, it's Biot-Savart law describing given any kind of little chunk of current, we can always calculate what our magnetic field is going to be. So currents create magnetic fields. That is an experimental fact. Historically, these two people, Biot and Savart, deduced an equivalent result by carefully doing experiments. They followed after the original discovery, what he discovered in lecture that if you run a current through a wire, you can deflect a compass needle. So following that experiment, following that discovery, they did a careful experiment to calculate, okay, exactly how much B field is produced by this current. So let's think of Coulomb's law. So this is describing the amount of E field produced by a single point charge, or in this case, a point charge dq, right? And this is little dq. And at some, from the source to your field, curly R, and it's producing a little E field dE. So this is telling me, okay, so this is my source and this is my field, and how much field is produced by the source. So Biot-Savart is having sort of the equivalent of that status in the magnetic fields. So Biot-Savart, as experiment find out, here is your little I, the L. So instead of putting our vectors on I, we're going to put our vectors on dl, and the direction of dl is going to be the current, which way the current is flowing. Okay, so I dl is this way, and let's say you have some kind of field over there. You want to evaluate the B field. Again, from your source to your point, you have your curly R, and then from Biot-Savart that gives you the B field. So dB, due to this little chunk of current, is mu naught over 4 pi I dl plus r hat over r squared. Okay. Now, if you write that in using integral format, then that's going to be mu naught over 4 pi the integral of I dl plus r. Now, this is the source, you can put a prime on it, over r squared. Okay. So like what we just did there, okay, so you have a wire, you have a little section of dl, you have a current flowing, and this is your origin, and this is the field of interest. So in this figure, we wanted to be able to write out curly R, and I have a few options for you to choose. Okay. So you have A, B, C, D, 4 different vectors, or maybe none of these. Which of these vectors correctly represent the script R vector or direction? Okay. All right, so 10 more seconds. All right, so I'm going to go ahead and end this. Okay, very good. I'm glad to see that the majority of you voted correctly for the curly R. Okay, so you don't always have to start out with R minus R prime. You can, but if you remember what curly R represents, is a vector pointing from your source to your field. So we can draw this vector right away, right? So you can see that A gives you a vector pointing from the source, right? Little chunk of current to the field of interest. So that's going to be A. Now you could get this from R minus R prime. So we can label R and R prime on our diagram. So which one of these do you think represent R? A, B, C, D?
B.
Yes, so that's your position of your field, right? That is B, vector B. So that's your R. And which one of these represent R prime?
C.
It's going to be choice C. That's going to be the position of where the source is. So it'll be from origin to the source, so that's R prime. And you can see indeed following the head to tail method, indeed R minus R prime give you a vector A. Okay, so A is correct. Okay, so going above a little bit, just want to add a little bit information on what these constants are. So the constant mu naught over 4 pi is equal to 10 to the negative 7 Newton per ampere squared. And recall in electrostatics, we have epsilon, right? Epsilon. And that is the permittivity of free space. So this is like the magnetic counterpart for the same constant, right? So this is the magnetic partner for the epsilon naught. And we call mu naught over 4 pi to represent the permeability of free space. And you probably also recall mu naught and epsilon is related to the speed of light, right? They combine together to give you the speed of light. Mu naught has the so sometimes we just don't say mu naught, we just simply divide 4 pi, so we don't have to say mu naught is 4 pi times 10 to the negative 7, because in the calculation you have to divide it by 4 pi anyway. It has the units of Newton per meter, and that's also Tesla times meter over ampere. All right, but all of that, I don't think you need to memorize, because we can always derive the units from units that we know. Right, for example, if you don't recall how they're all related, you can start with force is QV cross P, and you can plug in newtons, plug in coulomb. Now coulomb becomes current times time, right? This is coulomb, and this is meters per second, and then coulomb per second give you the current amp, and this give you Tesla. So you can always figure out how they're related. You don't have to memorize it. Okay, so now let's further on try to use Biot-Savart. The status of Biot-Savart and the usage of Biot-Savart is like doing direct integration for calculate your E field. So if you know there's a little chunk that gives this much dE, and you can always integrate whatever shape you have to get your total E field. And likewise, you can always do the integration and find out what your total E field has to be. So they have sort of the same status. So we know that this is representing the curly R, and now let's find out the B field. So given this little current distribution, right, current flowing to the left-hand side, you have a P above the wire. Using Biot-Savart, can you find out the direction of the B field at this point P that's created by the current in DL? Okay. So you need to do a DL cross R, and I'm just going to draw what you had previously for you. This is a script dot that you just did, right? Okay. So you need to do a DL cross R. All right. So I let you, here I'm gonna vote again because we still have quite a few questions left. Maybe we'll save our discussion time for later question. This one, I believe we could just do it here. So I'm gonna go ahead and open up the pool. All right, so I gathered majority of the vote. So just a few more seconds. If you haven't voted, please put in. All right, let's take a look at this together. So what is the direction for your B field? I believe we need to do a cross product, right? So majority of you voted for C. Very good. That is the into the page. Anybody would like to remind us how to do a cross product to figure out the DL cross R? How do we do that?
Is it just using the right-hand rule?
Yes, just use the right-hand rule. Yes, so your DL here is, so it doesn't really matter if your two vectors are not perpendicular to each other, as long as they define a plane and you know your thumb are going to be perpendicular to the plane, right? DL is pointing to the left and DR is this way. So is if you cross it over to the other side, you can see your thumb has to be pointing into the page. Very good. So that is the correct direction for the DB, right? Okay, so now what we actually going to do is let's work out the example of using Biot-Savart to find out the B field produced by a current carrying wire. I believe you still already know the results. We have used those multiple times in intro physics, but let's remind ourselves to see how do we derive that again. Okay, so this is the example we're going to do today. Is simply a straight wire, a long wire with a current I. So let's say we have a straight long wire carrying a current I in the Z direction. Okay,
Professor, I don't think your screen is, I think your screen is frozen. Oh, there, never mind. There you go.
Oh, wait. Yeah, it was gone, I believe. Thank you. But is it back? It's not back yet, is it?
It's back.
Okay. Okay, very good. Okay, so this is Z, and I'm gonna put X and Y here. And I have a current, right? Flowing in this direction. Okay. So I'm interested in finding out what is the magnetic field point produced at this point P over here. And that is going to be our vector. Okay, so we're going to find B at point P. All right, so we need to find out the curly R. Also, we need to label our source as your DL. So let's do that. So by looking at a little chunk of current over here, and that's DL. Okay. And also, you can see that it's probably easier if we use cylindrical coordinates because we have this kind of a long wire. So I'm going to call this P is at a radius S away from your center. And you can see because my current is on the Z axis, I can label my source is located at Z prime location, right? So this is at, so even though I have drawn it really long, I'm doing very exaggerating, but it's really just at one location that is simply Z prime. So perhaps right now what I can do is I'm going to shrink it down to a point. Now later on we'll work on this, expand this a little bit later. So right now to avoid confusion, okay, so what I'm gonna do, this is your current, but I'm going to simply look at a little chunk DL, and that's located at Z prime, okay? All right. So recall Biot-Savart have deduced this relationship between current and the magnetic field mu naught over 4 pi. Current I is a constant, dl cross r hat over r squared. Okay, so we're going to use cylindrical coordinates. Okay, and in this case, you can see that dl is on the z direction, so dl prime I'm going to rewrite using the z prime. Okay, and also dl plus r. So let's reduce this. What is dl plus r? dl is a unit length, so it doesn't have, it has a magnitude of 1. R is also a unit vector, right? This r hat, it's a magnitude of 1. So it's 1 times 1. What we need is the angle between them. So the angle between them is, this is your dl, this is your r, this is your r, right? You see, from source to field, and this is the angle between them. I'm gonna call it alpha prime. So dl cross r becomes what? Becomes dl, I'm sorry, it just becomes dl times 1 times sine of alpha prime. Okay, r is a unit length, dl is not. dl still this little length, you need to carry it over in order to do your integral later. So this is how I reduced my cross product, okay, into dl times 1 times sine theta, sine angle. So, okay, and you have to reduce this one, r squared. And you can look at this in this triangle, r squared is going to be, how do I do this? You have s squared plus, you need this particular length, right? And what is this length? So P is at height Z, and this is at height Z prime. So this little length is going to be Z minus Z prime, right? So this little length is going to be Z minus Z prime. Is this. So my R is going to be S squared plus Z minus Z prime squared. And also sine of alpha prime is going to be S over R, basically S over R. So you have represented all of these quantities that you need, and you're ready to do the integration. Okay, so dB so you can see my B, no matter where your chunk is always in the Z direction. And no matter what you do, the cross product, your B is always pointing into the page, right? So my B is all in the same direction. I don't have to worry about breaking it down into components. So they're all in the same direction. I'm ready to do my integration. So B is mu naught times I over 4 pi. Okay, and on the top, I have, they plug in the sine theta in sine alpha in here. You get S dz prime, dl prime become dz prime, divided by r squared times r squared times r cubed. So you get s squared plus z minus z prime squared to the power of 3 halves. Okay, that's r cubed. And what are your integration limits? Now, you can see that you can do this from just say Z1 to Z2, right? If you have a section, this can calculate any kind of length. Let's say your wire is not infinite, it's a finite length. So you have a lower limit and an upper limit. You can simply put in the location of your bottom of the wire and the top of the wire as in Z1 over Z2. You can put in negative infinity to infinity if that's the case. In this case, we are going to do a little bit different switch so that allow us to easily calculate infinite wires. So instead of doing dz, we're going to look at an angle. Okay, so if you, so here from Mathematica, you know that if you have this kind of relationship, if you try to do this integration, the result's going to be x over a squared, square root of a squared plus x squared. So I'm going to use this result right away. Directly put in your integration, and that becomes mu naught I over 4 pi. Over S. So what happens? Okay, so let me not write it so fast. I'm going to do 2 steps instead of 1. So this integration will give us, your S is still here, right? So S is still S. And that integration gives me this, which is going to be, my X in here is my Z prime minus Z. Okay, that's my X. And A is my S. So A squared is S squared, okay? And what's over here is going to be square root of S squared plus Z prime minus Z squared. Okay, so this is what I should get. Okay, and you can see I cancel this, I get the 1 over S over here. So mu naught I over 4 pi S Z prime minus Z S squared plus S Z prime minus Z square root of that. Okay, of course you have your limit Z1 to Z2, Z1 to Z2. Okay, so at this point, I'm going to plug in Z1 or Z2. I'm going to now blow up that little section we did not draw very big. So this is our DL, this is our DL. And you can see that the lower limit, sorry, this is my entire wire, not the little section. This is just my wire. And you have a lower limit Z1 and you have an upper limit of Z2. Okay, so it's on the Z-axis. And this is my S.
Question?
Yeah.
Can you scroll up a little bit, please?
Here?
Yes. There's also a question in the chat.
Okay. 1 second.
Okay, I got it. Thank you.
Yeah, why does z and z prime switch? You can see because my integration is dz prime. Okay, this is what I'm integrating. So I need to do z prime minus z is dz prime. I cannot do dz, see, because dz is not what I'm integrating over. I'm integrating over the source. And I switched z prime and z on the denominator because it doesn't matter. This is equivalent to z prime minus z squared, right? Because it's a squared. Does that make sense? Did I answer your question? Okay. Well, thank you for asking that. All right. Okay, so taking a look at this diagram, you can see, okay, let's define this one. This, if you're looking at this right here, you can define an alpha angle. If you're looking at your little chunk here, you can define another alpha angle, right? So that it turned out the cosine alpha is going to be z minus z1 over this guy. Okay. So because of this definition, we can rewrite this integration using cosine of alphas instead of the z's. And that's easier when we are dealing with a long wire later on, you will see. So this becomes cosine alpha 1 minus cosine of alpha 2. Okay, because the first term is z2 minus z over this. Okay, so z2 minus z is the negative cosine alpha 2, right? So that's why I have the negative cosine over 2 and the minus the other one, so become plus cosine alpha 1. Okay, so and then of course this is into the page. Okay, so let's see what would happen if we extend the wire to from infinity, negative infinity to infinity. So as you can see, if I lower my bottom or lower limit to here, and this is your alpha 1. If I lower it even more, this is your alpha 1. If I lower it even more, this is your alpha 1. So what do you think the alpha 1 become if I extend this to negative infinity? You see this angle is getting smaller and smaller, right? So what would alpha 1 become if I extend the lower limit to negative infinity?
So the cosine of alpha 1 should become 1.
Yes, so alpha 1 is pi or 0 if you have an infinite wire. Very good. Okay, so now let's look at alpha 2. Alpha 2 is this. Now, if your wire extend up, this is alpha 2. And the higher, the bigger that you go, alpha 2 become bigger. So what does alpha 2 become if you have an infinity of the wire?
Minus cosine of alpha 2 becomes minus 1.
Yeah, it becomes pi. Very good. So cosine alpha 1 becomes cosine 0 minus cosine pi. And 1 minus minus 1 is 2. So this becomes 2 for infinite wire. So I have derived mu naught I over 4 pi s times 2 becomes mu naught I over 2 pi s. Does that look familiar? So into the page is y. Does that look familiar for a current wire? I hope it does. And as you still recall, if you can use Ampere's law as we do in the next topic, you can get this results like in 2 seconds. So mu naught I over 2 pi s. This is something we are familiar with. Okay, now if your current is half infinite, so let's say you have a current wire and the current extend to infinity in this direction, but not in this direction, and you're evaluating your current here right at the bottom P over here, then the alpha 1 becomes pi over 2, and this becomes half of what your infinite wire has become. So your B for a half wire is going to be mu naught I over 4 pi s. Okay. So here we have a question that's kind of like a half wire. So you have this current that's been sort of folded into a 90-degree angle. You have a current flowing here and then going downward. You're evaluating your B right at this point shown. Yeah. Okay. It's at a distance s away from the corner. So which of these correctly represents the magnitude of the B field here? All right. I'll let you guys go ahead and have a discussion. Okay. All right, so let's go for another 10 seconds. Okay, all right, so let's take a look at the results. I'm gonna go ahead and close it. Pretty much tied between B and C. Now the question is, do you think this is more like a half wire or is an infinite long wire? All right. So if I have, and I'm gonna draw another situation to see if you think it's going to be equivalent. If this wire did not bend, if this wire simply just keep going like this. Do you think these two will have the same result or different?
Different.
Yeah, different. You can think of, okay, now I bend it. What if you can think of using the limits. What if you bend your wire or rotate it to be 100% perpendicular to your original? If you have made your wire to be entirely sort of running in this direction. So if your wire is in this direction, are you going to have a B field here? You can think about Biot-Savart. Biot-Savart is B is going to be in the direction of DL cross R. Okay, so DL is in this direction. Your R, in this case, from your source to your field of interest. Now your source and your field of interest are all in the same direction. Your R is also sort of in this direction. So DL and your R, your source and your separation vector are now in the same direction. Cross product of those two same directions is going to give you 0. Right, so this little section is not going to produce any B field here. All that contribution is coming from here. And you can see you can use the results we did here. It's kind of like a half wire, which is mu naught over 4 pi s, which is half of an infinite wire result. So C is correct. Okay, so let's do a quick review of the pre-lecture that you did. Array is something we are going to discuss in our next class. But here, first, let's try to label all these vectors. So let's label, okay, vector A. What does vector A represent? From the origin to a field point. So that should be my R, right? Vector B, from your origin to a little section of the wire. So that's your source. From field to the source is a location of your source. That's the R prime. Vector C is from, again, source to the field. That's the query R. Right, so we can label all of these. Okay. All right, so I don't think we have time to do this, so we're going to save it for the next class. We will try to calculate the B field at the center of the current here, like a loop, due to this kind of current distribution. We'll find the B at the center using Biot-Savart. Okay, you probably realize we cannot use Ampere's law. You can think about why cannot use Ampere's law, but we can always use Biot-Savart. So the first question would be, okay, so how do we reduce this cross product? So you can think about it later in after class, or we can look at it together on Wednesday. All right, so that's all we have for today. I will see you everyone on Wednesday. Have a good rest of the day.
You too. Thank you, Dr. Ryan.
Thank you, Dr. Ryan.
Thank you, Dr. Ryan.
Bye-bye.
Thank you, Dr. Ryan.
Thank you, Dr. Ryan. Have a nice day.
Thank you. Bye, everyone.